This is the first in a series of videos that introduces the simplex method, which is another way of solving linear programming problems, and it has the advantage of not requiring us to graph the feasible region. Now that's useful, especially when the problem has lots of variables, because although it's not too hard to graph inequalities in two variables, it becomes much more difficult with three and impossible with four or more variables. So the simplex method allows us to solve linear programming problems without graphing. Instead, we're going to express the problem using matrices, and the matrix can be very large without any difficulty. You can express lots of inequalities and lots of variables just by using a larger matrix, whereas it's very hard to draw a four-dimensional graph. So let's get started. The simplex method, first of all, can only be used, at least the way we're going to learn it here, on what's called a standard maximization problem. So that means we'll be limiting the type of linear programming problems which we look at using the simplex method. So standard maximization problem has three requirements. First, the function we're trying to maximize, which we call the objective function, we have to be trying to maximize it, not minimize it. It turns out there are ways to use the simplex method for minimizing, but that's not the approach we're going to take with this series of videos. Another requirement is that we have to know that the variables involved must be non-negative. So somewhere in the problem we need to know that x is greater than or equal to 0, y is greater than or equal to 0, etc. if there are more than two variables. So that has to be one of the constraints, and typically that is a real-world constraint anyway. For example, if you're trying to decide how many of each type of product to buy, well, you can't buy a negative number of products. So for practical purposes, this constraint usually exists anyway. And then the third issue we have to have in order to call it a standard problem is that all of the other constraints have to be able to be expressed this way as an inequality. We can have coefficients in front of each of the variables. So I'm writing this in terms of three variables, but there could be more. So there could be 4, 5, 110 unknowns. But when we express the constraints, the inequalities, we have to be able to write it as the combination of those variables is less than or equal to. It's important. This cannot be greater than or equal to. That's not allowed. And the right side here has to be a number that's not negative. So let's look at a couple of examples. First of all, this is a maximization problem. We're finding the maximum value of this function. We do see that there are constraints telling us all the variables in this problem have to be non-negative, so that's good. So that's so far two of the conditions. And then the third condition, for calling it a standard problem, is also satisfied. If we look at each one of these other constraints, we have a combination of the variables on the left side, less than or equal to, that's good. And the right side of these inequalities are positive numbers, 1 and 4. So this is indeed a standard maximization problem, which means if we were faced with this question of finding the maximum value with these constraints, we would be able to apply the simplex method as we're going to learn it. Let's look at another example. We're asked to find the maximum value of some function subject to some constraints. Well, we are looking for a maximum. That's one of the conditions that we require for the simplex method. However, the other two conditions are not met in this example. First of all, we're told that x and z are non-negative, but there's no such constraint for y. So it's possible that y could be less than 0. And if that's the case, then the simplex method will not apply. Similarly, the other constraints have problems with them. The first one has an inequality facing the wrong way, and the second one has a right side that's not greater than or equal to 0. This right side is negative. So this is not a standard maximization problem, which means this is not the kind of question we will be able to attack using the simplex method. So again, this is our list of conditions for calling something a standard maximization problem. The first condition is satisfied, but as we can see, the second condition is not satisfied because we don't know that y is non-negative. And the third condition is not satisfied for different reasons. Wrong direction of the inequality for the first constraint, wrong sign of the right side for the second constraint. Now, if we do have a standard maximization problem, then we can use the simplex method. And the next thing we need to do is to discuss how we're going to express the simplex method, how we're going to express the maximization problem as a matrix and apply this new method. Remember that a matrix can be used to express a system of equations. For example, if we're doing Gauss-Jordan elimination, we know how to write down the augmented matrix that represents that system. And so we're going to do something similar here, except we're starting with inequalities instead of equations. And so we have to change things into equations. And the way we do that is by introducing extra variables. These extra variables are called slack variables because we think of them as taking up the slack and changing the inequality into an equation. Here's what we mean. Consider this inequality. So this is saying that whatever number you get by evaluating the left side could be smaller than 4, right? So it could be 2 or 3.5. It won't be bigger, but it could be smaller. Now, if I want to change this into an equation, an equal sign, what I can do is add a little bit to the left side. So by introducing an extra variable here that represents some positive number, I'm making the left side bigger. And so if the left side used to be less than 4, I can add a little bit to make it equal 4. So this s is called a slack variable. It changes the inequality to an equality. If there's any difference between the left side and the right side, s accounts for that difference, so it takes up the slack. So again, all we're doing is adding a non-negative value to the left side so that the two things will be equal. We don't know what value that is. It turns out we will discover that value from applying the simplex method. But this is our first step. We introduce slack variables for each of the constraints in order to make them into equations. And we'll need a different variable for each equation. Then we take the objective function and we rewrite it in this form with all of the variables on the left side. So it's as if we take the formula for our objective function and move all the variables and their coefficients to the left side. So notice that they change sign when we move them to the left side. We want to put everything on the same side as the function that represented, the symbol that represented the function itself. And we want to make sure that that has a plus sign in front of it. So we move everything else to the other side and end up with an equation that looks like this. So then we'll take all of those equations, the equations that we got from the constraint inequalities by adding slack variables, and the equation that we get from rewriting the formula for the objective function. We take all of those equations and express that system of equations using a matrix. So for example, if we are asked to maximize this function subject to these constraints. And we should add here, since we're going to use the simplex method, that we were really also going to need to know that the variables are non-negative. But I'm leaving that out of our description so that we can focus on the primary constraints, which are the ones we need to change into equations. The first thing we do is introduce slack variables for each inequality. So this first inequality, we introduce a slack variable s so that we can write an equation instead. For the second inequality, we introduce a new slack variable, t. We take the objective function and move all of the variables to the same side as the symbol that represents the function. And so that formula for the objective function becomes this equation with the right side equal to 0. So now I have two equations that came from our constraints, one equation that came from the objective function. We take all of those equations with the one from the objective function last, and we change that into an augmented matrix. So just like when we are applying the Gauss-Jordan elimination method for solving a system of equations, we are simply taking the coefficients from each equation and converting them into the entries for rows of a matrix in order. Notice how we're careful to line up all of the variables. So this is the entire row or column that corresponds to S, and this is the entire column that corresponds to coefficients of t, and so on. So once we've done this, this is called a simplex matrix or a simplex tableau. Tableau is a French word for table, which is just another way of describing the layout of a matrix. And so this is our starting point. Once we've got to this, we are ready to start applying the simplex method itself.